Hello and welcome to Chemistry with Dr. Clark. In the video today, I'd like to talk about writing the names and chemical formulas for ionic compounds. Now, this is the second video in like a three-part series on naming and writing chemical formulas for ionic compounds. Today, or in this video, I'd like to talk about what happens if you have both group A and group B elements present in your ion. Now, if you didn't watch the first video does focus exclusively on group A elements. So if you're having a bit of trouble with naming ionic compounds, you may want to stop this video here, go back and look at the one that focuses only on group A, and then come back. And the third video in the three-part series will be what happens if you have group A and group B and polyatomics. Okay, so a little bit of a review from the first video. An ionic compound forms when you have a cation and an anion, positively charged, negatively charged, because a positive and a negative charge will attract one another electrostatically. Okay, so the minute you have a positive and negative near each other, they'll automatically link up. Now, when you're writing the name, the metal always goes first, and there's no name change. So if I look at my examples here, on the periodic table, iron is written as iron. In the name of this thing, it's still written as iron. On the periodic table, titanium is written as titanium. When I write it as part of an ionic compound, it's still written as titanium. The nonmetal is always named second, and it always has a name change. So if you looked up on the periodic table, chloride would be listed as chlorine. So on the periodic table, as an atom, it's listed as chlorine, but the minute it becomes an ion and part of an ionic compound, the ending changes to "ide." Same thing for the sulfur. Right on the periodic table, it would be listed as sulfur, but the minute it becomes an ion and becomes part of an ionic compound, it changes its name to sulfide. Okay, so the original endings of the nonmetals change into ides when they become ions and part of ionic compounds. Now, the biggest difference between dealing with exclusively group A and starting to bring in the group B elements is that the group B elements have more than one possible charge. Okay, so if we talk about iron, irons can form iron 2+, but iron can also form iron 3+. There's two possible charges for iron, which makes it a little confusing, right? If I told you that you had an iron ion, how do you know which one, right? Is it the iron 2+ or the iron 3+? In order for me to tell you which one you have, we use Roman numerals. When I say that I have an iron 2, what I'm doing is telling you the charge. It's an iron 2+. When I tell you that you have an iron 3, that means you have a 3+. Okay, so there are some metals on the periodic table that can form more than one possible ion. Titanium is another one. Titanium can be titanium 2+ or it can be titanium 4+. And the only way that you're going to know which one is if the question tells it to you. So in this question, it told you it's titanium 4. So it would be this titanium. Okay. Now, not all metal ions do this, only some of them, which means that when you start using Roman numerals, you have to use them in the correct places. Like if we talk about sodium. So if I talked about sodium chloride, good old table salt, NaCl. I don't have to say that this is sodium and put a Roman numeral behind it because sodium has only one possible charge. Sodium can only be a 1+. If you have only one possible charge, then you don't get Roman numerals. Okay? So this is one of those you have to be careful, because if you're supposed to have Roman numerals and you leave them out, that's a mistake. If you're not supposed to have Roman numerals and you put them in, that's also a mistake. Okay, so you have to know when to use them and you have to know when not to use them. All right, so let's take a look at our B elements. So what I've got here is just a piece of the periodic table, right? Group 1A and 2A would be over here on the left, And then I've got group 3A, 4A, 5A, 6A, 7A would be over on the right. The reason why I focus on this piece of the table, because the majority of the metals that can form more than one ion are the Bs. So right here in the middle of my periodic table, there are the columns, the groups labeled with Bs. 3B, 4B, 5B, 6B, 7B. 8B covers 3 columns, 1B and 2B. These are your transition metals. And the general rule is, if you're a transition metal, you need to have Roman numerals, because your transition metals, virtually all of them, have more than one possible charge. Now, like any good rule, there are exceptions, and you've got to know the exceptions. So if you look at your transition metals, okay, this is in the middle of your periodic table, it's all of your B columns. There are 2 of them that do not require Roman numerals. Silver doesn't need a Roman numeral, and zinc does not need a Roman numeral. And the reason is that both of them only have one possible ion. If you're going to be talking about silver, silver can only form a silver 1+. That's the only possible ion it can form. And if you're talking about zinc, zinc can only form a 2+. That's the only possible ion it can have. Here in the transition metal group, from here to here, everything else has more than one possible charge. Chromium can be chromium 2+ or 3+. Cobalt can be cobalt 2+ or 3+. Vanadium's wild. Vanadium can be 1+, 2+, 3+, or 4+, right? Vanadium has lots of possibilities. So everything else in the transition metals will have more than one charge, which means everything else in the transition metals will require Roman numerals. The only 2 that you're not allowed to use Roman numeral for are silver and zinc. Now, if nobody's going to use Roman numerals for these 2, that means nobody's going to tell you what the charge is, which means that you have to memorize what the charge is. You have to know that when silver becomes an ion, it's going to be silver 1+. You have to know that when zinc forms an ion, it's going to be a zinc 2+. Now, your periodic table has attempted to help you. Now, if you've looked at the numbering here in the Bs, it should seem a little unusual to you. It's like it starts with 3B, 4B, 5B, 6B, 7B, and then kind of circles around to 1B and 2B. Right? You would expect them to be just 1, 2, 3, 4, 5, 6, 7, 8. The part of the reason for that, silver is a 1+, and it's in the 1B group. Okay, 1B plus 1, it helps you to remember. Which group is the zinc in? The zinc is in the 2B. And what's the charge that a zinc can have? It can have a 2+. Okay, that's not an accident. It's meant to help you remember them. So these 2 are your exceptions. If you see silver or zinc in a question, you are not allowed to use Roman numerals for it. Now, there's a second set of exceptions. Things that require Roman numerals, transition metals, only here in the Bs. But there are 2 metals that are outside of the transition metals that also need Roman numerals. These 2 right here, tin and lead. Tin and lead are not part of your transition metals, but they can both form ions with more than one charge. Tin likes to do tin 2+ and tin 4+. Lead likes to do lead 2+ and lead 4+. Okay, so the rule is transition metals require Roman numerals, except silver and zinc. Except tin and lead. They need Roman numerals even though they're not transition metals. Okay, so these 4 you have to remember are going to give you some trouble, right? 2 of them should have Roman numerals, but they don't. 2 of them should not have Roman numerals, but they do. Okay, so make sure that you remember those. Other than that, other than having some Roman numerals thrown in, the rules for naming the ionic compounds and writing chemical formulas for ionic compounds, pretty much the same for the A elements and the B elements, right? There's not a whole lot of difference. It's just that the B's generally require Roman numerals. So let's take a look at an example or two. All right, so I have a full periodic table hiding down here in the bottom. Let me see if I can dig it out. Now, it is a little small because it is a more complete periodic table. It does show my A elements and it does show my transition elements, right? So it's kind of all crushed together there. Now, if you have watched the first video on naming ionic compounds and writing their formulas, you'll see that for the A elements, we do like to write the charges that they're going to have right above the column. So if you're in group number 1, group number 1 likes to have charges of +1. If you're in group number 2, when they form ions, they like to have charges of +2. If you're in group number 3, you like to have a charge of +3. Group number 4 does not like to do ions, so we're just going to cross that one out for this video. When you get up to group number 5, you got 5 valence electrons, you'd really like to have 8. So if you gain 3 more electrons, you're gaining 3 negative charges. That's a -3. If you're in group number 6, you've got 6 valence electrons. You'd really like to have 8, so you have to gain 2 more. If you gain 2 electrons, that's a -2. And if you're in group number 7, you've got 7 valence electrons. You'd like to have 8, which means you have to gain 1 electron. If you gain 1 negative charge, that's a -1. And these are my inert or noble gases, and they don't do ions either. Okay, so for my A elements, +1, +2, +3, -3, -2, -1. You really should memorize those. These here are my transition elements right here in the middle. And for the most part, those are the ones that need Roman numerals. Okay, from here to here. So let's do what we did when we were naming the A group ionic compounds. We're going to write the ionic formula for the first ion. We're going to write the ionic formula for the second one, and then we're going to put them together. Now, I purposefully chose manganese because on the periodic table there is both manganese and magnesium. Okay, they're both here. The magnesium is here. The manganese is here. And the two names sound the same, right? It's very easy to mix them up. They also spell kind of the same. So if you have a magnesium or a manganese, you have to be really careful that you don't accidentally choose the wrong one. Okay, so it is manganese. Here's my manganese. So the symbol is an Mn. Now, it is a transition metal. In the transition metals, they can have more than one charge. And the only way that you're going to know which one is if the problem tells you. So because this has a Roman numeral 2 after it, that means the charge on this manganese is going to be a 2+. Now the fluoride. Let's highlight our dividing line between metals and nonmetals, right? Your periodic table has a staircase. Everything on this side is a metal. That'll be the first part of your ionic compound. Everything on the right side of the staircase would be your nonmetal. So this would be the second part of your ionic compound. So if I'm going looking for fluoride, fluoride is going to be over here in this corner. Now I can see that I have a fluorine, and just remember the names change. So even though this is a fluorine and this is a fluoride, they are talking about the same thing. Fluorine is when it's an atom and it's electrically neutral. Fluoride is when it's actually gained this charge, right? Because originally the fluorine would have 9 protons and 9 electrons, electrically neutral. But when it becomes an ion, it gains an electron, so it becomes a -1 charge. Okay, that's why there's a name change. Now, the easiest way to do this is rewrite your two ions, manganese and fluoride, and we use the charges to tell us how many. So if the charge on the manganese is a 2+, that means you need 2 fluorides. If the charge on the fluoride is a -1, that means you need 1 manganese. And we did cover the taking of charges and switching them in the first part of the video series on naming and writing the chemical formulas for ionic compounds. Okay, so if this is giving you a little bit of trouble, you might want to pause, go back and watch the first part of this series. Okay, now let's talk about why this makes sense. Your manganese is a 2+, and I'm telling you that you have 2 fluorides. First fluoride, second fluoride. The total amount of positive charge is +2. The total amount of negative charge now is also 2, right? +2, -2. And in an ionic compound, the total amount of positive and the total amount of negative has got to match up. Now, we also said that chemists we're lazy people. I don't want to write anything that I don't have to. I guess the approved word would be concise. We're concise people. Really, we're just lazy people. I don't want to write that one. By putting down Mn, I am basically saying there's a manganese. Why should I also have to say that there's one of them, right? Just writing down Mn implies that there's at least one. So for this, I'm going to write MnF2 because the fact that I've wrote Mn implies that there's at least one. So this would be the chemical formula for manganese 2-fluoride. 1 manganese, 2 fluorides in order to make the charges balance. All right, let's talk vanadium. Vanadium would be located right here. You'll notice no name change. First name never changes. Vanadium, vanadium, symbol V. It is a transition metal. And because it's a transition metal, you really can't tell what the charge is going to be. So I have to tell you, in this one, IV means 4. So this has a charge of 4. This is vanadium 4+. Iodide is a nonmetal. It's found over here. If I look at my table, I can find an iodine, right, with a name change. So I, on the periodic table, is an atom. That's an iodine. The minute that you give it the charge, now it's an iodide and it's an ion. If we do the fancy little switch thing, switch the 4 and the 1. So if I list my 2 elements, V and I, because there's a -1 charge on the iodide, I'm going to have 1 vanadium. Because there's a +4 charge on the vanadium, I'm going to have 4 of them. And I don't really like to write the 1, so I just drop it and call this Vi4. Vanadium 4 iodide. And once again, if you want to make sure that the charges match, vanadium's a 4+. Vanadium 4+. I'm now telling you that you need 4 iodides. So let's draw iodide 4 times. Iodide, 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 iodide. Right? That's what Vi4 means. 1 vanadium, 4 iodides. Total amount of positive charge is 4+. Total amount of negative charge is 1-. Amount of positive and negative balance. Now, that's the reason why when I put the 2 of them together, I don't write their charges anymore, right? When they were separate, when I had the vanadium here all by itself, I told you that it was a 4+. When I wrote the iodine by itself, I told you that it was an I-. But when I put them together, I don't put the charges in anymore because when they come together, the charges cancel out. Okay, so I don't need to write them. This vanadium still has a +4 charge. Each one of the iodines still has a -1 charge, but because they're together, we consider the charges as canceled out, so we don't write them. All right, let's move this up and take a look at the next example. The next example is a lead chloride. Now, when I look at this, I'm like, oh, hold it. Lead is not a transition metal, right? My transition metals are right here. Lead's not there. Lead is, where's my lead? Ooh, cross my lead out. Here's my lead right here. Remember we said these are exceptions. They actually do get Roman numerals because they do form more than one ion. I may have gotten a little carried away when I canceled out this column, because really when I was talking about things that don't like to form ions, it was just the carbon, the silicon, and the germanium. It's really only the first three that I should have canceled out, but I went overboard. All right, so lead is one of the exceptions, and it does tell me what the charge is. So Pb, since there's Roman numeral 2, that's a lead 2+. Chloride is a nonmetal, so chloride would be here. Now again, periodic table says it's a chlorine because atoms. That would be a chlorine atom. The minute that you give it a charge, now it becomes a chloride. If we do our little trick where we take the charges and use them to help us determine how many. So Pb, because the charge on a chloride is -1, I'm going to get one of them. Cl, because the charge on a lead is a 2, I'm going to get a 2, right? 1 lead, 2 for the chloride. And I've gotten smarter. Instead of writing the 1 here and then rewriting it, I just left the 1 out. All right, let's talk about gold 3 oxide. If you go looking for gold, gold is right here, Au. It is a transition metal, and therefore it has Roman numerals, and the Roman numerals tell you what the charge is. So the charge on this gold is going to be a gold 3+. Oxygen's a nonmetal. The minute that you give it a charge, it changes from being an oxygen to an oxide. So my oxide would have a charge of -2. Okay, if we take the two numbers and switch them, this means that I have 2 of the golds. Charge on oxygen was 2, so that means my golds have 2. And because the charge on the gold was 3, it means I have 3 oxygens. And again, you can see why this is if I write them out, right? This tells me that I have 2 golds. So that's an Au3+ and an Au3+. It tells me that I have 3 oxygens. That's an O2-, an O2-, and an O2-. Total amount of positive charge is 6. Total amount of negative charge is 6. Right? Positive 6, negative 6. They balance. In order to balance out the positives and the negatives, I needed 2 of the golds and 3 of the oxygens. All right, let's try 2 more. At this point, I should probably mention you need to know your way around your periodic table. Okay? So you need to take some time just to look it over and find things. Like for gold, the symbol for gold is Au. It has nothing to do with its English name, right? It's based on its original older Latin or Greek name, right? So for some of these, they may be a little hard to find. So it's worth taking some time to just familiarize yourself. Make it a game with one of your classmates or someone that's also doing this course, right? You have your periodic table, they have theirs. You name an element, you say niobium. And then they have to find it on their periodic table as fast as they can. It is worth taking the time to learn where the elements are. It'll save you so much time here. Like when I go looking for chromium, I'm looking for chromium. Chromium's here. It's a whole lot faster if I know the general spot where chromium is instead of having to look through the entire table to find it. Okay, chromium is a transition metal. The Roman numerals tell me the charge. So this is a Cr2+. The oxide comes from here, so that's an O2-. And then I realize that I've got a perfect match, right? I've got a +2 and a -2. They're like perfect for each other. If you've got a perfect match, you only need one of each, right? 1 chromium and 1 oxygen. The +2 and the -2 cancel each other out. That would be my formula. But now you should be thinking, hold on a second there, Dr. Clark. What about if I like doing this crisscross thing? What about if I like taking the numbers and switching them? That's the way I've decided to do it. Well, that's okay. You're allowed to do that. Because the charge on an oxide is 2-, that gives you 2 chromiums. Because the charge on a chromium is a 2+, that gives you 2 oxides. Now, this is science. You can't have two different answers for the same problem, right? If I asked for the formula for chromium 2 oxide, you can't be able to give me two. So the rule that we've got is that these little numbers, these subscripts, have to be a lowest terms, lowest ratio. So think math. If I told you that you had 2 to 2 in math as a ratio, 2 to 2 reduces to 1 to 1. So I could rewrite this as a CR101, right? Instead of 2 to 2, 1 to 1. And we don't like to write ones, so if we drop the ones, you just get CRO. Therefore, there is only one answer for this problem, and it's right here. All right, let's try another one just like it. If I look up titanium 3, titanium is here. It is a transition metal. It has more than one charge, and the problem tells you what the charge is. So this would be Ti 3+. The second element is always a nonmetal, so it'll always be in this corner of your periodic table. And if you look up phosphide, the closest that you're going to find is phosphorus. As the atom, it's phosphorus. When you turn it into the ion, it becomes phosphide. As an atom, it has no charge, electrically neutral. But as an ion, it has a -3 charge. And you can see that I've given you another perfect pair. You've got 3 positives, you've got 3 negatives, they just match perfectly. If they match perfectly, you only need one of each, TiP. But if you've decided that you really like taking the charges and using those to figure out how many, that'll work for you too. Ti and P. Charge on a phosphide is 3-, you get 3 titaniums. Charge on a titanium is 3+, so you get 3 phosphides. And this is a 3 to 3 ratio. 3 to 3 reduces to 1 to 1. So that gives you 1 titanium and 1 phosphide. And we can drop the ones, so this becomes this. Writing the chemical formulas for group A and B elements, pretty much the same as writing the chemical formulas for just group A elements. You find it, you figure out the 2 charges, and you switch them. If you happen to have subscripts that are not lowest terms, then you just turn them into lowest terms. All right, let's say we'd like to go in the opposite direction. Here I gave you the gave you the name, and I asked for the formula. What about if I give you the formula and I ask for the name? Okay, for this, it is a little bit more difficult because for these, you're going to have to decide, A, do I need Roman numerals? And B, what is the Roman numeral? Right, so it's like, do I need them? And what is it? Okay, so let's take a look at the first one here. You've got CO3N2. I am looking for an element that has the symbol CO. So if I go looking through all of my elements, I see that CO is here. It's cobalt. So that's COBALT. Now, this cobalt is a transition metal, which means it's most likely going to need Roman numerals. Is it one of our 2 exceptions? No. So cobalt will need Roman numerals. I don't exactly know what it is yet, but I know that it does. Let's skip the Roman numerals and just finish naming it. The second element is an N. So if I come over here and I look up N, N goes with nitrogen. Now I know that I can't use the name as it is, right? The nonmetals change their name. So instead of a nitrogen, I'm going to have a nitride, right? Ends in "ide." Now I'd like to know the charge on that cobalt. Well, it turns out the easiest way to do that is with this little crisscross thing. Where do the little numbers that tell you how many come from? They come from the charges, right? The fact here that I had 1 manganese is related to the charge on fluoride. Here that I had 2 fluorides is based on the charge on the manganese. So what I need to do is do my crisscross thing, but in reverse. So instead of taking them and turning them into how many, I need to take the how many and turn it back into the charge. So let's do this. If I write my cobalt and my nitrogen, let's take those two little subscript numbers and put them back where they came from. Since you have two nitrogens, that means the original charge on the cobalt was a 2+. Since you have three cobalts, that means the original charge on the nitrogen was 3-. Now, please remember that as numbers, like how many cobalts and how many nitrogens, they're both positive. But when you put them back up as charges, some of them become positive and some of them become negative. The metal will always be positive, the nonmetal will always be negative. Okay, so the charge on the cobalt is 2+. That means this is a cobalt 2. That's how you figure out the charge. All right, let's try the next one. If I look up Hg, Hg is mercury right here. Name of the first one does not change. So if it's mercury in the periodic table, it's going to be mercury here. There we go. Now, mercury is in the transition metals. So there's a good chance it needs a Roman numeral. Is it one of the two exceptions? No. Which means it definitely needs Roman numerals. Now, I'm going to leave a space for it, but I'm going to come back afterwards and actually figure it out. Let's name the second element. The second element is a Cl. So if I come over here and I look for Cl's, Cl is chlorine. But remember, the second name changes. So instead of a chlorine, it's going to be a chloride. Now, I'd like to know which Roman numeral. So let's take this thing apart. It was originally a mercury and a chlorine. The reason why you have two chlorides here is because the mercury had a charge of 2+. Now, if you look here, you're like, I don't know how many mercuries I had. There's no number, right? There's no number there. But remember, we're lazy people. If there's no number, that means the number was originally a 1. So if you have 1 mercury, that means the charge on the chlorine is a -1. Metals are positive, nonmetals are negative. So this is going to be a mercury 2 chloride. All right, let's do the third one here. If I go looking for Sn, Sn is right here. Unfortunately, I crossed it out, but that's where Sn is. It's tin. So that's tin. Now you got to ask yourself, do I need a Roman numeral? Tin is right here. Tin is not in my transition metals, which means that there's a pretty good chance that it does not need a Roman numeral. But then you remember, oh, even though they're not transition metals, tin and lead, Sn and Pb, they are exceptions. Even though they're not transition metals, they do need Roman numerals. That's why your exceptions are important. And it turns out that people that teach chemistry and people who give you like problems to do in chemistry, we love the exceptions. You're going to see lots of silvers, lots of zincs, lots of leads, and lots of tins. Like, they are our favorites. So you're going to see a lot of those. Make sure you memorize them. Okay, so they are an exception, which means they do need their Roman numerals, but let's leave it till the end. The second element is N. That would be nitrogen. Here it is. And again, its name in the periodic table is nitrogen, but when it's an ion, it's a nitride. And let's do the same trick where we crisscross. Okay, here's my Sn, here's my N. I had 3 tins, so that was a 3- charge on the nitrogen. I had 2 nitrogens, that means it was a +2 charge on the tin, right? So this would be a tin 2. Now you will notice for all 3 of these, I never really told you anything about the numbers, right? Yes, I did have to use the 2 to figure out the charge on the cobalt, but I ever tell you the charge or the number on a nitride? Nope. Same deal here, right? I had to use the 2 to figure out the charge on the mercury for the Roman numeral, But did I ever tell you about the charge on a chloride or how many? That there was 2 chlorides or that its charge is -1? No. When you are naming ionic compounds, you just need to tell me the name of the first one, the name of the second one, and put in the Roman numerals if you need it. You do not have to tell me how many of each. That is not part of naming ionic compounds. All right, let's move down to some that are a little more difficult. Let's say that I would like to name this thing. Okay, at this point, you're feeling a bit more confident. You're like, okay, Ti, if I go looking for Ti's, Ti is titanium. Okay, so titanium. Titanium is a transition metal, so it's probably going to need a Roman numeral. It's not one of the exceptions, so it definitely needs a Roman numeral. S, if I look it up, is for sulfur. Sulfur is the atom. Sulfide is the ion. Okay. Now, we're going to do the little crisscross thing. Okay, so remember, if there's no numbers, that means they're both ones. So this is titanium. This is sulfur. The reason why you have 1 titanium is because the charge on a sulfur is 1 minus. The reason why you have 1 sulfur or 1 sulfide is the charge on a titanium is 1 plus. Now I'm hoping that when you look at this, you're like, ooh, Dr. Clark, that doesn't look right. Titanium, you don't know what the charge is supposed to be. But look at that sulfide. Does sulfide actually have a -1 charge? No, sulfide should have a -2 charge. That's not right. The problem here is that whoever wrote the original formula did this. Remember how when we got 2 to 2, we reduced it to 1 to 1? And when we got 3 to 3, we reduced it to 1 to 1? Okay? That's what happened here. Somebody reduced this to 1 to 1. Really, the charge on a sulfur is a -2. That's the real charge on sulfur. So instead of it being a 1 to 1, it was originally a 2 to 2. This is titanium 2. Now for these problems here, that's an important thing. Okay, it's something that you didn't have to worry about when you were doing only group A's. When you move into group B and you're looking for the Roman numeral, you've got to be careful that the charges are right. That it hasn't been like a 3 to 3 that got reduced to a 1 to 1. So if we go back up and check, here I said nitrogen had a 3- charge, and nitride does have a 3- charge. This one's correct, so this is good. I said chloride has a -1 charge. Does chloride actually have a -1 charge? Yes, so these are correct. Here I said nitride had a -3 charge. Does nitride have a -3? Yes, so this is correct. Okay, when you are switching them back and you're showing the charges, you always need to check that the nonmetal charge is correct. That's the only way you're going to know if it got reduced. Okay, so let's try another one like that. If I look at this one here, FeN. Okay, so Fe is iron. That would be iron. It's a transition metal. It is not one of the exceptions, so it will need Roman numerals. N is nitrogen, but it becomes nitride. So nitride. To get the Roman numerals, I'm going to take the how many of each and switch them back. So this is Fe, this is N. If there is no number, that means this is a 1 and a 1. So the reason why you have 1 iron is because the charge on the nitrogen was -1. The reason why you have 1 nitrogen is because the charge on the iron was a 1 plus. Now if we check, nitride is right here. Nitride should have a charge of -3, but I'm saying it's got a charge of -1. That's not right, which means that this has been reduced. So let's put the right charge in. the right charge is a -3. So if it's been reduced to 1 to 1, that means originally it was a 3 to 3, right? 1 to 1, 3 to 3 is the same. So this would be an iron 3. Now, if you do get a pair where it's like 1 to 1, see how the titanium and the sulfide was 1 to 1? Iron and nitrogen was 1 to 1? Those should make your spidey sense tingle. You should be like, ooh, I think maybe this one was reduced, so I have to be really careful. The reason I've thrown in this example is because it doesn't always work for just 1 to 1s. Turns out this one here has also been reduced. Okay, so if we go looking for names, Ti is titanium. So Titanium. O is oxide. So oxide. Titanium is a transition metal. It's not one of the exceptions, so it needs Roman numerals. And if we do our crisscross thing, okay, so here's my titanium, here's my oxygen. You have 1 titanium, right? If there's no number, it's a 1. So if you've got 1 titanium, that means the charge on the oxygen was 1 minus. If you've got 2 oxygens, that means the charge on the titanium is a 2 plus. Now you check. Does oxide actually have a charge of -1? No, it has a charge of -2. Right, so the charge here is -2. That means that this has been reduced. It went from 2 to something down to 1 to 2. That's like a doubling. This would also be a doubling because 4 to 2 is the same as 2 to 1, right? You divide the 4 by 2, you divide the 2 by 2. So this would actually be 4 plus and 2 minus. So this is titanium 4 oxide. Okay? The reduction to the lowest ratio usually ends up in a 1 to 1, right? Usually when you reduce, you end up with 1 to 1, 1 to 1. If you look at the examples from earlier, right? It was 2 to 2 turned into 1 to 1. 3 to 3 turned into 1 to 1. But you can get unusual cases where it's like a 4 to 2 turning into a 2 to 1. So when you're doing these, naming and writing formulas, if you're naming, you always have to ask yourself, does the metal need a Roman numeral? If it does, what is the Roman numeral? And when you go looking for it, did I get the right charge on the nonmetal? Because the charge on the nonmetal, if that one's right, it will tell you if the charge on the metal is correct. All right, let's take one more minute and take a look at a couple of more. The question that I wanted to address here was, do you need Roman numerals or not? Because the last 6 examples all required them. So if I was going to do this, Zn. If I go looking for Zn, Zn is right here. That is zinc. Zinc is a transition metal. You're like, transition metals? Most of them have Roman numerals. Is zinc one of the exceptions? Yes, it is. Because zinc is an exception, it doesn't need Roman numerals. Gone. S was sulfur, becomes sulfide, and you're done, right? If you don't need Roman numerals, don't put in Roman numerals. All right, take a look at this one here. This is an SrBr2. If I go looking for Sr, Sr is right here, strontium. So this is strontium. Do you need Roman numerals for strontium? Answer is no. Strontium is not a transition metal, right? Transition metals are here. So strontium is not a transition metal, which means it probably does not need a Roman numeral. Is it one of the exceptions that lives outside the transition metals, like tin and lead? Nope. That means strontium does not need a Roman numeral. Okay, do not put in Roman numerals if you don't need them. Br, here on my periodic table it's bromine, but as part of an ion it's a bromide. Okay. And our last one. Ag is silver. So that is silver. Silver is a transition metal, but it's an exception, right? Transition metals need Roman numerals except for silver and zinc. If it doesn't need a Roman numeral, don't write one. Okay, P, here on my periodic table, is phosphorus, but you have to change its ending, so this would become phosphide. Okay, these last three, none of them needed Roman numerals. If you put in Roman numerals, that makes the name incorrect. Okay, so do not put in Roman numerals unless they are required. Okay, so this is part 2 of a 3-part series on naming and writing chemical formulas for ionic compounds. Part 1 only focused on group A elements, these. Part 2 focused on my transition metals. These are my group B elements. The third part includes polyatomic ions. So if you need to know how to name things, write formulas for things that have polyatomic ions, you should join me for the part 3 of the series. Once again, I'd like to say thank you for joining me here at Chemistry with Dr. Clark.